Hello and welcome to this lesson in our study of linear algebra. Our topic for today is a method of least squares. Okay, so in this lesson, you will deal with systems of equation. Okay, so when you have system of equation, there are three possible solutions. Okay, either you get unique solution, infinitely many solution, or no solution. Okay, so a system of equations said to have a unique solution if the rank of the augmented matrix is the same as the rank of the coefficient matrix. Okay, it also have no solution if the rank of the augmented matrix is greater than the rank of the coefficient matrix, and it will have infinitely many solutions if the rank of the augmented coefficient matrix is greater than or equal to the rank of the augmented matrix. Okay, so we say that systems of equation with unique solution are also known as consistent solution. Consistent solution. Okay, so with consistent solution you can solve it using the Cramer's rule or any method, elimination, substitution. Okay, but when you have a system of equation whereby you get the solution is you get infinitely many solution or no solution, that's we say that system of equation have inconsistent solution. Okay, they have inconsistent solution. So when you have a problem like this, we are required to use the method of least squares to solve this problem. Okay, either when you have a system of equation with either no solution or infinitely many solutions, have to use the method of least squares, okay, to solve this problem. So when you have system of equation, you can write it in this form. That's ax equals to b, where b is a constant terms or the values at the right hand side of the equal sign. A is a coefficient matrix. Okay, and since this will have inconsistent system, it means that the coefficient matrix is singular. Okay, or in other words, the coefficient matrix have a determinant of 0, or the columns or the rows of the coefficient matrix A are linearly dependent. Take note of that. So when you have A, you express we have system of equation with inconsistent solution. You can write it as ax equals to b. Then the best way to solve such system is to find x that makes ax closest to b. Okay, that's an approximation of ax to b. The smaller the distance between a and ax given by this the distance, right, the better the approximation. So with this we have to find our x hat. Okay, where x hat is the closest point. But before that, let's consider some definition. So if A is an m by n matrix, okay, and B is a finite dimension, vector of finite dimension, a least square solution of ax equals to b is an x hat, okay, such that the norm of or the distance between a minus nx ax hat is less than or equal to the distance between b and ax hat, ax, okay, for every x in Rn. Okay, then we say that x hat is what the least square solution. Okay, that will minimize or that will bring b closer to ax. Okay, so this is how we solve it. This we are not going through the proofs. Okay, so you have solution to general least square problem. You apply the orthogonal decomposition theorem. That's when you have any two non-zero vectors of finite dimension, let's say y and u, okay, where in a given subspace w, okay, then you can express y, or you can decompose y into two terms, the sum of two different vectors. One is a product of u and the other orthogonal to u. Okay, and in other words, you can express y as what? Y hat plus z, where y hat is the orthogonal projection of y onto u, and z is a component of y orthogonal to u. Okay, so when you go through the process, you get this one. You should take notice of this. This is what you are going to solve for the least square solution. That's A transpose A x hat equals to A transpose B. Okay, so we are going to use this formula to solve our problem. Okay, so now let's look at our first example. Let's look at our first example. Let's look at our first example. Okay, so we have to find the least square solution of the inconsistent, this is one word, okay, of the inconsistent system ax equals to b. For A, this is what? 3 by 2 matrix, have 3 rows, 2 columns, and B 2 0 11. Okay, so to solve this, we use this formula: A transpose A x hat is given by A transpose B. Okay, so x hat is given by A transpose A inverse A transpose B. Okay, so first of all, we find our transpose of A. Okay, so the transpose of A is given by this, that's 401021. Okay, then we multiply by B, or we multiply by A. So we first solve for A transpose B. Okay, so we multiply row by column. So 4 times 2 is 8 plus 0 plus 11, that's what? 19. Then 0 times 2 is 0 plus 0 plus 11, so you get 19 11. Okay, then A transpose A is given by this, so 4 times 4 is 16 plus 0 plus 1, you get 17 here. 4 times 0 is 0 plus 0 plus 1, gets 1 here. This is 0 plus 0 plus 1, get 1. 0 plus 4 plus 1, which is 5. Okay, so therefore we can find our least square solution. Okay, so we have A transpose A, we have A transpose B. So therefore the least square solution is given by A transpose A, or inverse, times A transpose B. So we find the inverse of A transpose A, that's 1 over the determinant times the adjoint. Okay, so the determinant of A transpose A is given by 17 times 5. 17 times 5 minus 1. 17 times 5 is 85. 85 minus 1 is 84, so that's the determinant. And for the adjoint, we swap the elements in the leading diagonals. Okay, we swap the element on the leading diagonals. So we swap 17 and 5, so we have 517. Then we negate the element on the other diagonal, so we have negative 1 negative 1. Okay, then we multiply by A transpose B. You have our A transpose B to be 1911. Okay, so when we solve this, we get 1 2. So therefore our least square solution to this problem is what? 1 2. Okay, now let's discuss another important thing here. Okay, let's talk about least square error. Okay, the least square error is given by b minus ax hat, okay, where x has the least square solution. Okay, so this is a continuation to the question. This is the second part of the question. So to find the least square error, you need to know your least square solution. Okay, and least square error is given by the distance between b and the what ax hat, where x hat is the least square solution. Okay, so we know our x hat, we know our b, we know our a. So first of all, we multiply matrix A by the least square solution. So our matrix A is given by this, we multiply by the least square solution. Okay, so when you simplify this, you get 4, 4, 3. That's 4 times 1. You multiply each row in the matrix A by the column of, or by vector x hat, which is the least square solution. Okay, so you have 4 plus 0, which is 4. 0 plus 4 is 4. 1 plus 2 is 3. Okay, so therefore b minus ax hat, we have b to be 2, 0, 11. Okay, this is 11. Okay, 2, 0, 11 minus 4, 4, 3. 2 minus 4 is negative 2. 0 minus 4 is minus 4. Then 11 minus 3 is 8. Then the norm of this is given by this, and when you simplify, you get root 84 error. Okay, root 84 error. Root 84 error. We also have another alternate method of solving this problem. So when you have this, you express the columns of matrix A. So you find b hat such that b hat is a orthogonal projection of b onto the columns of matrix A. Okay, b hat is what? The orthogonal projection of b onto the columns of matrix A. A have two columns. That's, this is the first column and this is the second column. Okay, so you find the orthogonal projection of b onto the columns of A. Okay, so when you do that, you get this. Okay, then you simplify this. That's ax hat times b hat. Okay, ax hat times b hat. So x hat is a list of weights that will build b out of the columns of A, and therefore the weight to place on the columns of A to what produce b hat. Okay, this is not clear. Okay, so this is another way of solving the problem. That's the alternative way of solving the problem. Okay, so this is an exercise, and try your hands on this question. Okay, and try your hands on these questions. So with the first one, let's discuss it. We are not going to solve it, but let me help you so that you might not find difficulty when you are trying your hands on it. So with the first one, we have to find the least square solution of this. Okay, so we use this formula: A transpose ax hat is given by A transpose B. Okay, so least square solution is x has given by A transpose A inverse A transpose B. Okay, so first of all, you transpose this A. When you transpose this A, the first row will be, this column will be the first row, that's minus 1, 2, 1, and the second column will be the second row. Okay, so this 3 by 2 matrix will change towards 2 by 3 matrix. Okay, then after that, you multiply the transpose of A by matrix A. Okay, then you find the inverse. The inverse is 1 over the determinant times the adjoint of A, times the adjoint of A transpose A. Then you also multiply the transpose of A by B. Okay, then we multiply the inverse of transpose A by A transpose B. That will help you to find the least square solution. Then with the second question, we have to determine the least square error in the least square solution. The least square error is given by the norm of b minus ax hat. So before you can be able to solve for the least square error, you should be able to find the least square solution, okay, using this same formula. So after obtaining your least square solution, we multiply the least square solution by matrix A, okay, or you pre-multiply the least square solution by matrix A, then we subtract it from matrix B, that's the distance, okay. Then after that, you find the norm. Thank you for watching this video.